In this video, we're going to look at the phenomenon of buoyancy and the buoyant force. So if you've ever been in water, and if specifically if you've ever been floating in water, maybe you're just lying on your back in a swimming pool or you're in a boat or anything along those lines, you have experienced buoyancy whether or not you know it. The buoyant force on an object submerged in a fluid is understandable by beginning to look at that object submerged in the fluid and asking ourselves, okay, well, if it's in a fluid, it's under pressure. So what are the forces that make up that pressure look like? So I'm just going to recall to your mind that pressure increases with depth in a fluid. So here I have an object. I've made it a cube, but it doesn't have to be a cube. And I've put it in a fluid. I don't know what this fluid is. I've drawn some waves up here. Maybe it's water. It certainly doesn't have to be water. It could be another liquid. It could be air. It could be any gas, because all of those are considered to be fluids. And buoyancy happens in a fluid. It doesn't have to be in water, but that's normally where we encounter it in daily life. So if this helps you to think of it as water, feel free. So I've drawn in some of the forces that are acting, right? At the top, and I should say that I've drawn this geometrically very simple, but it does not have to be geometrically simple. What we're going to find is that you can, no matter what shape of your object, you'll be able to decompose any forces that act on it into perpendicular and horizontal components. And so you're going to see the same effect no matter what shape the object is. All right, now with that said, I have the forces up on top, and the forces are exerted normal to the surface. And I've drawn them here, and I've drawn them as small arrows because I'm not very deep in the fluid. Right? Remember, pressure varies with depth. What that means is that the forces exerted on this object vary with depth. They vary proportionally to depth. On the sides, I've taken that into account. So the force that's acting up here is small, and then as I move down, the force is larger and larger and larger until I get to the bottom of the object. Again, it doesn't really matter the shape of this object. I will find that there are horizontal components that do the same exact behavior. And I would like you to notice that because of that the forces are always exerted normal to the surface, what I get on each side are forces that are going to cancel in pairs. This point on the side is the same depth as this point on the side, and so this force and this force are going to cancel. So I actually get no contributions from both sides taken together. These forces are going to cancel in pairs. But that is not the case for the bottom and the top, right? The top is always at a shallower depth than the bottom. And so I will always get a larger pressure at the bottom of this object, which means the forces exerted on it are bigger than the ones at the top. So if I have this force top and then this force at the bottom, I'm going to have to say that force at the bottom is always greater, in magnitude, of course, in magnitude, than the force at the top. I have to say in magnitude because one of these is positive and one of them is negative. That depends on what sort of coordinate system you set up. But what I always find is that the effect here is that there is a force on this object that is upwards. No matter the fluid, no matter the object, I get a force upwards. Now, that may or may not be the total force acting on an object. In fact, it's probably not. This object is going to have mass, which means gravity is going to be pulling it down. So, and I could have other forces acting on it as well. So we sometimes, all of us will say the net force is upwards. What we mean is the net force only taking into account the forces from pressure. If you take into account all the forces acting on an object, it may or may not be upwards. If you drop a rock into a pond, it sinks, therefore the net force is downward. But there is a buoyant force on that rock that acts upward. There's always a buoyant force. It comes from pressure. It comes from the fact that pressure increases with depth in a fluid. And it is always pointed up for that same reason. All right, so that's the origin of the buoyant force, how do we characterize it? Well, we turn to Archimedes, who was an ancient Greek mathematician, and we'd call him a scientist these days. I suppose he would have called himself a natural philosopher. There's some stories about how Archimedes discovered these things. They may or may not be apocryphal, but at the very least, we have the Archimedes principle. Which says this: the buoyant force acting on an object in a fluid is equal to the weight of the displaced fluid. The weight of the displaced fluid. So let's talk about a couple things in here. If you're in my class, you know that I don't really like weight. I don't really like using the word weight because it's a little non-specific. You find plenty of people that disagree with me on that. The textbook we're using uses it as a substitute for the force of gravity. I specifically don't like it for that reason, because it is not equal to the force of gravity if you are accelerating. So you got to take this with a grain of salt. With that said, it is always true in this case. What we're saying is that the force of gravity acting on the displaced fluid, if that fluid is at equilibrium, is what we're looking for. So weight works just fine here. It's going to be an mg no matter what. That's what we're substituting in for the weight of the displaced fluid. Will be an mg, where m is the mass of the displaced fluid, and we know what g is. All right, well, what do we mean by displaced? Well, if I'm putting something in water or in any fluid, I've got to move that stuff out of the way. So let's say that I take a cube, and this cube has a side of 1 meter all the way around. Well, okay. If I put this then in, let's say, some water, any fluid will do. If I put this in a fluid, how much fluid do I displace? And what do I mean by even displacing it? Well, to put this in this fluid, I got to move some of that fluid out of the way. Now, because of the way fluids work, that fluid is going to fill in every gap and every space around this thing. And so there won't be any, air pockets left, or, at least how I've drawn it here. There won't be any space that's not in this cube that is not encased in the fluid. In this case, I could have it maybe sticking halfway out of the water, and then I'd have to do a different calculation. But the idea is, if I put this into a fluid, I got to move some of that fluid out of the way to fit it in. How much fluid do I move out of the way? Well, I move out of the way exactly the same volume of fluid as of my object. And so what is the volume of this thing? Well, 1 meter per side. I think I can do that in my head. I get 1 cubic meter, which means what I have moved out of the way is 1 cubic meter of, in this case, water, or whatever fluid I'm putting it in. So to determine the buoyant force acting on this object, what I now need to do is determine how much the force of gravity acts on 1 cubic meter of water, right? We know that that's going to be mg. So the mass of 1 cubic meter of water times the acceleration due to gravity is what I'm going to need to determine to find the buoyant force. All right. So the buoyant force acting on an object, which is always up, is equal to the weight of the displaced fluid. All right. That is Archimedes' principle. Let's take this farther and see if we can determine some clues on to how to work problems here, and how to actually characterize things a little bit better than this. Because the problem I would find here is, well, how am I supposed to know what the mass is of 1 cubic meter of water? I might be able to look that up, but what if I have, some strange substance and some strange dimensions, and I have no idea what the mass of that stuff is? Well, to solve that problem, we're going to go back to our definition of density. Our volumetric mass density is defined as a mass per unit volume. 3 lines means definition. What that means is I can rearrange this to solve for the mass as rho v. Again, if you're in my class, you've heard me say if you see rho v, you should think of that as a mass. That's what it is. And so if I'm looking for the weight of that displaced water, I can say mass of the water times little g. I can rewrite this as density of the water times the volume of the water times little g. And that actually turns out to be more useful because I can look this up on a chart. In fact, if you've been through some chemistry classes, you probably know what the density of water is. It's pretty easy. If not, we'll see it later. And then if I'm talking about the volume, well, remember what's doing the displacing moves out of its way an amount of the fluid exactly equal to the volume of the object. And so that's usually something that I can measure. Let me say that again because that's a pretty critical distinction. This is the volume of the water that's been displaced, but that has to be equal to the volume of the object that did the displacing in the first place. So for this example, my cube, I would actually rewrite this as the density of the water times the volume of my object times little g. And just to complete it, I guess, the density of the water times 1 cubic meter. In this specific case, that was what the volume of my object was. It's 1 cubic meter. So the fact that this volume of the water turns into the volume of the object usually makes this pretty solvable because you can just measure the object. Notice this also, if I remember what density is, let me rewrite the density here as mass per unit volume times the volume of the object times little g. I would probably never write it like this if I was solving a problem where this is the volume of the fluid, right? And this is the mass of the fluid. Notice what this also does is it will increase the buoyant force or decrease it. It says the buoyant force goes proportionally to the mass of the fluid. It says it goes proportionally to the density of the fluid. What that means is that if you have a really dense fluid, you get a greater buoyant force. So if you're trying to increase the buoyant force, you need to increase the density of the fluid. If any of you have ever heard of the Dead Sea, the Dead Sea is a sea in the Middle East where water flows in, but it has no outlet. The water just evaporates. Of course, when it evaporates, it leaves behind all sorts of minerals, most specifically salts. The Dead Sea is the saltiest body of water on the face of the earth. I've never been to the Dead Sea. I've never swam in it, but from what I understand, it's actually really difficult to go underwater there. It's almost impossible to sink because of all of the dissolved salt in the water. That increases the mass per unit volume. You're adding salt in there. It increases the density of that fluid and thereby increases the buoyant force pretty significantly. If any of you ever go to the Dead Sea, you feel like swimming in it, just remember your physics, right? It's easy to swim in because the mass of that of any particular volume of the fluid is greater because of all the dissolved salt content. So that's Archimedes' principle in a nutshell. There's one sort of variation on this that we usually encounter when we're solving problems, and it turns out to be a particularly interesting case, and so let's look at it. Let me take a fluid in which I have partially submerged something. Now, if something is going to float in a fluid, this is what it's going to look like. So I have this portion of this object that's submerged and this portion that's not. And let's say that the percentage submerged is some beta, just as a placeholder, right? It'll be different for every situation. To characterize this system, you might be asked different things about it, but to characterize this system, let's draw a free body diagram of it. Now, I'm going to assume that this thing is in equilibrium. It's neither sinking nor rising. It has done all that, and it's come to this position of equilibrium. And so what I can say is that the force of gravity acting down on this object has got to be equal to the buoyant force acting on that object. Go away. Got a little bug here. All right, so Newton's second law just gives me this. The mass, and I'm going to write this way, the mass of the object times little g is equal to the buoyant force. But we know what the buoyant force is equal to. That's equal to the weight of the displaced fluid. So now I can rewrite this as mass of the object, g, that's the force of gravity acting on this object, is equal to rho of the fluid times volume of the fluid, right? That's my mass of the fluid times g. All right, all I did was I substituted in for the buoyant force the rho of the fluid times the volume of the displaced fluid times g. Displaced fluid is what's important here. That's Archimedes' principle. Okay, well, immediately I can get rid of the accelerations due to gravity. And now let's remember that the volume of the displaced fluid has to be equal to the volume of the object that's doing the displacing. Okay? Now, in this case, the entire volume is not displacing it, but this percentage is displacing it. So on the right-hand side, this has to be equal to rho of the fluid times a certain percentage of the volume of the object. The displaced fluid, the volume of that displaced fluid has got to be equal to this percentage of the object. I can write that as beta, my percent submerged, times the volume of the object. So this beta volume of the object is the volume of the displaced fluid. On the other side, it will be helpful if I rewrite the mass of the object as the density of the object times the volume of the object, right? If I want to know the density of anything, I take its mass and I divide it by its volume. So over here, I just rewrote the mass, as I've said before. If you see rho v, you read that as a mass. So the mass of the object's got to equal the density of the object times its own volume. So on the left-hand side, I have everything in terms of the object. On the right-hand side, I've turned my fluid expressions into one involving the fluid and the object by recognizing that the volume of the displaced fluid's got to be equal to the volume of the object that's displacing it. And so I can get rid of that. And now I have this expression that's just in terms of the densities and the percentage submerged. So if I solve this for the percentage submerged, actually, interestingly, that gives me a ratio of the densities. That's really interesting because you can then use this, if you know where this comes from, you can then use this to tell simple things like if something will float in a particular fluid or not, or if something will sink or rise or stay where it is. Right. Let's imagine that the density of the object is the same as the density of the fluid. That makes this expression 1. If I go back to this expression now, what I will find is that rho object is equal to rho object, V object, is equal to rho fluid times 1 times V object. What that means is that this thing will just stay, it will be completely submerged, but it'll just sort of sit there floating. It won't move up, it won't move down. If I put it here, it'll stay here. If I move it to here, it'll stay here. That means the buoyant force and the gravitational force exactly cancel each other at the precise point when this thing is fully submerged. What if the rho of the object is less than the rho of the fluid? Well, then beta is less than 1, and that actually corresponds to this particular case. If beta is less than 1, if I hold this thing underwater and I let it go, it'll rise up and then it'll come to the surface, eventually coming into an equilibrium where this percentage is submerged. What happens if rho of the object is greater than rho of the fluid? Well, beta is greater than 1, and this expression stops making any sense, but what we can tell is that this thing will go to the bottom. Right? If I hold it here and then I let it go, it's going to sink. It's not hard to think of examples for that. Rocks do this, right? Boats do what's in the picture. Rocks sink. We don't normally encounter anything with the same density, so the idea of putting something and moving it around and it just stays there is not something we normally see in everyday life. That's a very, very special case. Normally we see the two extremes. Beta is bigger than 1, which means the density of the object is greater than the density of the fluid, it sinks to the bottom. If the density of the object is less than the density of the fluid, it rises to the top. Think of styrofoam or corks or little plastic bobbers on fishing lines. They do that. But the weight on the fishing line, or a rock, or a solid piece of metal that's just, in one chunk, falls right down to the bottom. It sinks. You can tell what it's going to do just by examining the density both of the object and of the fluid in which you find it.